Good day everyone, my name is Leong Hui Min. Today I am sharing my proposal, Forecasting High Medical Expenses Using Machine Learning and Mixed Research Method. In simple terms, this study focuses on how machine learning integrated with a robust mixed method research design can significantly improve risk assessment accuracy. Ultimately, the goal is to provide data-driven insight that support fairer and more transparent insurance pricing decisions for all stakeholders. I have structured today's talks into 5 sessions. We will move from the research context and objective into my methodology design, followed by my data analysis strategy, and finally the implications and ethics of the works. Why is this research necessary? Globally, healthcare costs are rising rapidly. This is driven by aging populations and the increasing number of long-term health conditions. As a result, insurers are facing a difficult balance that must remain competitive yet financially sustainable. In Malaysia, the situation has become critical, as highlighted by the STAR. Medical inflation is growing faster than the general inflation. Premiums are projected to increase by 40 to 70%, which places significant pressure on both insurers and households. Therefore, there is an urgent need for more advanced forecasting tools. These tools can help stabilize the insurance market while also protecting affordability for consumers. The problem is that many insurers still rely on rigid traditional pricing model, even though machine learning has proven more effective. There is a practical gap in applying this advanced model to actually separate high cost from low cost policyholder in a way that informs real world pricing decisions. Now that we understand the problem, let's look at the research gap. To bridge this gap, I have 4 objectives: identifying risk factors, developing classification model, comparing their performance, and assessing how this insight and change underwriting decisions. My research question focuses on which factors are more predictive and how we can balance model accuracy with transparency. The frameworks illustrate how demographic and lifestyle variables interact to influence medical cost outcome. It examines these factors through the perspective of healthcare utilization's behavior, showing how different habits and characteristics can lead to various levels of medical expenses. Importantly, the model also considers modeling variables such as age and smoking status, which can significantly amplify or weaken the effect of other risks like BMI. Now that we have established the what and why of the problem, let's discuss the how. Choosing the right research method is vital because it determines how we collect data and, more importantly, how accurately we interpret our result. My study follows a structured mixed method research cycle. Why use a mixed method? Quantitative data gives us accuracy, but qualitative data gives us depth. By combining them, I achieve completeness using a circus of planning, collections, analysis, and interpretations to explain the why behind the numbers. Next, I will explain the methodology design. I'm using an explanatory sequential design. This means phase 1 is a quantitative machine learning analysis, which then directly guides the phase 2 qualitative interviews. The most vital part of the design is integration. By combining both quantitative and qualitative insight with our models, we arrive at our final goal: actionable insurance pricing decisions. As highlighted by Creswell and Creswell 2018, this approach helps ensure that the findings are not treated as black box, but instead supporting and validating by expert judgment and real-world insight. My quantitative phases use a structured health insurance dataset for KG. The independent variables include age, BMI, and region, while the goal is binary classifications, high cost versus low cost policyholders. To ensure models quality, I follow a strict pre-processing cycle, cleaning null or inconsistent records, encoding categorical data into numeric form, scaling variables like age and BMI, and performing an 80-20 train and test splits to prevent overfitting. By following this cycle, we ensure that our model's predictions are based on clean, balanced, and statistical sound information. One common challenge in the insurance database is class imbalance, where high cost cases are relatively rare. As shown in the before chart, the minority group, which represent a high cost policyholder, appear has only few scattered red points. If we train a machine learning model on this unbalanced data, the model train has to favor the majority group. It may report a high overall accuracy simply by predicting most people are low cost, but it would perform poorly in identifying the high-risk individual we actually need to detect. To address this issue, I apply smoke with generous synthetic minority samples rather than duplicating existing one. This helps balance the dataset, significantly improve the model's recall in detecting high-risk policyholders. Once the data is clean and balanced, we can move on to applying our proposed machine learning model. To ensure a fair, meaningful comparison, I selected 3 different algorithms, each with a distinct strength. Model A is a logistic regression, which serves as our baseline model. It is simple, transparent, and highly interpretable. This means we can clearly see how each variable influences the predictions. It acts as a benchmark, helping us understand how much improvement the more advanced model actually provides. Model B is random forest. Instead of relying on a single decision tree, it combines many trees and averages their result. This improves stability and reduces overfitting. It is especially effective in capturing the non-linear pattern commonly found in medical data. Model C is XGBoost, a powerful boosting algorithm. Unlike random forests, which build trees independently, XGBoost builds them sequentially, where which new tree learns from previous mistake. Is widely recognized for his strong predictive accuracy and include regularization techniques to control model complexity. By evaluating this tree model, we can identify which approach the best balance between accuracy, reliability when forecasting high-cost policyholder. I selected this model because they support sharp interpretability analysis. This enables us to move beyond traditional black box predictions and instead provide clear, explainable justification for each risk assessment. Such transparency is especially important in the insurance industry, where fairness and accountability are essential. After training the models, we evaluate them a multiple layer approach. Since our dataset is imbalanced and high cost cases, we cannot rely on accuracy alone. Our primary metric focuses on how well we detect high cost policy. F1 score balance precision and recall, making it highly suitable for imbalanced data. Recall is especially important for a business perspective because it measures how many high cost cases we correctly identify, helping people to reduce financial risk. We then review secondary metric for an overall performance review. Accuracy shows the general percentage of correct predictions, while ROC-AUC indicates how well the model separates high and low cost group regardless of threshold. Finally, the confusion metric provides a visual summary of true and false prediction, allow us to pinpoint where the model performs well and where the improvements are needed. In phase 2, I will conduct semi-structured interview with underwriters, actuaries, and claim analysts. This allows us to explore professional judgment and behavior factors that are not captured in the numeric database. To ensure a 360-degree views of the industry, we engage 3 key groups of participants: underwriters, who assess risk and make daily premium decisions; actuaries, who evaluate the long-term statistics and financial implications of this risk; claim analysts, who observe the real-world claim pattern and imaging customer behavior trend. The core purpose here is threefold: to understand the context and the behavioral influences that are not captured in the standard database, to provide a practical interpretations of our machine learning output, and finally to support the integrations of quantitative finding with a seasoned expert judgment. As the result at the bottom suggests, these qualitative insights are what truly enhance the interpretability and the world applicability of our predictive model. After the interview are completed, we move to a qualitative data analysis stage. The aim here is to find a behavioral pattern and insight that numbers alone may miss. I use a thematic analysis, which is a structured method for identifying a common themes across interview responses. This helps us understand professional judgment and decision making in insurance. The process involves 3 steps: open coding, Azure coding, selective coding. This is to ensure the reliability, and I will also use the tools like MVVote to organize the data, applying triangulations by comparing the view from different rows and conducting a member checking to confirm the interpretations with the participant. By combining this qualitative insight with the predictive model, we get a more complete and balanced understanding of medical cost forecasting. This stage represents the integrations of both machine predictions and expert insight from a more balanced and informed decision. From an ethical perspective, I am committed to data de-identification, bias mitigation, and ensure that the insurance premium remain fair and undiscriminatory. This study assumed that the medical cost trend remained relatively stable in near term. However, I also noticed several limitations, such as the absence of genetic or detailed clinical data. Despite this constraint, the research aimed to provide a scalable and evidence-based framework that supports more sustainable and fair insurance pricing decisions. In conclusion, this study demonstrated that combining machine learning with mixed method research can significantly improve the accuracy, fairness, and sustainability of health insurance pricing decisions. Despite this boundary, the research represents a vital step toward integrating data science with human experts. By addressing this challenge head-on, we can create more sustainable, transparent, and fair insurance pricing model for Malaysian market. Thank you for your attention. The reference listed key literature support the methodology choices in the study.